Okay, now that we've done derivatives, we're going to start trying to do the inverse problem. When this book was first published, this was actually chapter 3, but after their grant ran out, they wanted to make money, so they tried to make it the same order as everybody else. But it didn't win awards that way, it won awards this way, so this is what we're going to do. We're going to do chapter 5, which is on integrals, which is addressing the opposite question. So I'm going to just start reading a little. This says, in chapter 2, we thought hard about the questions. What can we say about the rate of a function if the function's rate is not constant? And how will we interpret it? And how could we apply it? In this chapter, chapter 5, we consider the main two components of what is called the inverse problem. What can we say about the original function if all we were given was the rate at any time t and a starting point? So in other words, in chapter 2, we went from the function to the rate. In chapter 5, we're going to try as hard as possible to go from the rate to the original function. In chapter 2, it was about slopes of tangent lines, but how do you unslope a tangent line? This is what this is about. So I'm just going to go to the second page. This is still basics. We're familiar with the formula distance equals rate times time, right? But the rate doesn't always have to be velocity. It's kind of weird. The example we're going to be going through today is how fast air is escaping from a balloon. For example, if air is escaping from a balloon at 2 cubic feet per second that has been escaping for 3 seconds, I can still multiply rate times time, right? So I'm going to get my 2 cubic feet per second times 3 seconds, and I get 6 cubic feet. Well, that's the amount of air that escaped during that time. It's not distance traveled. It is an amount of something, and it's actually what we're going to do. If we thought about it graphically, now this is again when the rate is constant, we could find the total distance traveled, or total escaped air in this case, or total whatever, is exactly equal to the area under the rate graph. In this particular example, you can see that if the rate was always 2 and we went from 1 to 4, the area would be 8. It would have kind of crazy units. For example, if this is in feet per second and this is in seconds, I multiply the feet per second times the seconds, and the units wouldn't be square anything. They'd be feet, which is exactly how it would work when the rate is constant. We'll skip over this stuff about the derivative for a day or two, then we'll come back and it'll make a lot more sense. What are we going to do when the rate is not constant? Well, what we did in chapter 2 is we zoomed in on the graph until the graph looked linear. That's the same thing as saying until the rate looked constant. Similarly here, we're going to zoom in on the rate graph until it looks constant. And then for a very short period, we're going to pretend that it really is constant. And any errors we make by pretending or lying that way, we'll try to fix later on. This procedure is so useful that many mathematicians have stated it as a principle, and then they generalized it to death. Basically, they're saying most functions are locally linear in most places. The rate version would say most rate functions are locally constant in most places. Now, one more thing about approximations. We're going to be doing approximations all chapter. That always involves two numbers, not just one. Because if someone gives you an estimate of something without telling you about how far off it is, it's actually a useless estimate. So when we do an approximation in this class, we either want an estimate of that tells us here's the estimate and the error is plus or minus something, or similarly, they could give us an upper bound, a number that we guarantee too big, and a lower bound, that's a number that's guaranteed too small. From that, we can get the error with the estimate with the plus or minus error, so that's not so bad. All right, so we're now ready to start our example, which we're going to do in the next little video.